Let's take a look at question number 1 from our AP Physics 2 Thermodynamics problem set. We see that we have a cylindrical can that has a cross-sectional area of 0.005 square meters and a length, or a height rather, of 0.15 meters. The can is filled with an ideal gas and covered with a loose cap. The gas is heated to 363 Kelvin, and some gas is allowed to escape the can so that the remaining gas reaches atmospheric pressure at 1.0 times 10 to the 5 pascals. The cap is now loosened, or tightened rather, and the gas is cooled to 298 Kelvin. What is the pressure of the cooled gas? Well, when we do a problem, whether it's free response or multiple choice, the very first thing we want to do is identify the concept. This is an example of an ideal gas law concept. Okay, we know this because it is referencing things such as temperature of the gas, pressure of the gas, and a certain volume of gas. Now, if the conditions ever change from one set of pressure, volume, and temperature to another possible concept in here would be combined gas law, which is really just ideal gas law applied to 2 different states of a gas. And so that's what we're going to be looking at to solve this problem. It wants to know the pressure of the cooled gas. So we're going to list some values here. Pressure 1, volume 1, temperature 1. Pressure 2, volume 2, temperature 2. Now the volume of the can never changes. So I'm going to essentially cancel the volume from both parts, because whatever I put here is going to be the same amount here. Well, I'm not going to bother calculating volume yet. I'm just going to cancel it from the whole thing. Pressure, P1, is 1.0 times 10 to the 5 pascals. 1 atmosphere, essentially. Okay? 1.0 times 10 to the 5 pascals. The temperature at that is 363 Kelvin. What is the pressure of the cooled gas? Well, we don't know. That's what we're looking for. The temperature of the cooled gas, well, the gas was allowed to cool to 298 Kelvin. Well, this is a combined gas law problem because it's ideal gas law at 2 different states of a gas. Pressure, volume, and temperature changes. So combined gas law equation is P1 times V1 over T1 equals P2 times V2 over T2. Since the volume stayed the same, we'll cancel volume from both parts of the equation. And we get P1 over T1 equals P2 over T2. Now, to make the equation easier to work with, take your cross products and eliminate the fraction. In other words, P1 times T2 equals P2 times T1. Now we're solving for P2, so we have to divide away T1. P2 would be 1 atmosphere of pressure, 1.0 times 10 to the 5 pascals, times T2, which is 298 Kelvin, over T1, which was 363 Kelvin. You'll notice the units of Kelvin cancel nicely. And our pressure is 8.2 times 10 to the 4 pascals, which would be less than an atmosphere of pressure. Part B, determine the upward force on the cap by the cooled gas inside the can. Well, how do we relate force to ideal gas law? Well, force relates to pressure in the idea that pressure is the force per unit area, and we are given the area. So we'll solve this for force. Force is equal to pressure times area. The cooled gas pressure, so this would be 8.2 times 10 to the 4 pascals times the area of 0.000, well, too many zeros, 0.05 square meters. That equates to about 410 newtons of force. And lastly, in part C, it says if the cap develops a leak, how many moles of air would enter the can as it reaches a final equilibrium at 298 Kelvin and increases to atmospheric pressure? Remember, we are at 8.2 times 10 to the 4 pascals of pressure, less than atmospheric pressure. So if air enters the can, it will build up the pressure to 1 atmosphere of pressure. Well, in this particular problem, nothing is really changing except the number of moles of gas and the pressure of gas. The temperature stays at 298, and the volume of the can does not increase or decrease. So the volume of gas is not going to change either. So this is an interesting example in terms of how we can use ideal gas law. Normally, PV equals nRT. That is the ideal gas law equation. However, if the number of moles change with any particular variable change, like pressure, volume, or temperature, then we could restate it like this. The change in pressure times volume, that does not change, is equal to the, I'll write this in a different letter, different color. The change in pressure times volume is equal to the number of moles, the change in the number of moles, times R times T. Now remember, R in the ideal gas law is a constant, and it's about 8.31 joules per mole Kelvin. You don't need to memorize it. This is just a number given on the AP exam. So we can use this as a modified version of ideal gas law to solve for the essential increase of gas. Delta N would represent the increase of air added to the can to match the increase in pressure. And we're going to solve for delta N. Delta N would essentially equal delta P times V over RT. Well, delta P would be 1.0 times 10 to the 5, that's 1 atmosphere of pressure, minus the 0.82 times 10 to the 4 pascals, that would be the pressure before the air enters the can, times the volume. Now, how do we get the volume? Well, that's going to be area, 0.005 square meters, times height, 0.15 meters. All of that is going to be divided by R, which is 8.31 joules per mole Kelvin, times that temperature of 298 Kelvin. And we're looking at about 5.45 times 10 to the negative 3 moles of gas. So that's how much air would have to enter the can in order for the pressure to be brought back up to atmospheric pressure.